All right, working 3.63. This is another problem dealing with balancing equations, but it presents as being a little bit more difficult for a student, and that's because of the wording for the problem, okay? In a previous problem, which was 3.58, you just had the skeletal chemical equation needed to balance it, okay? Meaning that you had all of the formulas for the compounds. In 3.63, not so easy. They basically describe to you what's going on in words and ask you to write the equation and then balance it. This is a good practice, okay, because it goes back to writing formulas, writing proper formulas for compounds. We're not going to get away from that, okay? We're going to see that throughout the semester. The first part A of this problem reads, lead 2 nitrate is an aqueous solution of that is added to an aqueous solution of potassium iodide. A reaction occurs to form solid lead 2 iodide and potassium nitrate solution. They want you to write a balanced chemical equation for this change, okay? Turns out that they're kind of nice to us because pretty soon here you're going to be asked to predict the products of reactions, and this is sort of a classical type of experiment or example of one of the types of reactions that you're going to learn about. It will be called a precipitation reaction. It's going to be a form of something called a double displacement reaction. Okay, precipitation reactions, they make solids in aqueous solution, typically insoluble solids, and that's how we predict the products. But we'll get to that in a little bit. Right now, we're just going to write the equation and balance it. So the problem tells us about lead 2 nitrate aqueous solution, or solution of that, okay? Well, if we're going to think about how to do this problem, we have to start off by figuring out how to write the formula for lead 2 nitrate. Now, I know it's lead 2. Let's given that in the problem, and it's also going to be an aqueous solution of that, so I'll write AQ. And it's dissolved up in water, surrounded by water molecules. And these ions really exist sort of floating around in solution. But that lead 2 is paired up with nitrate, at least in the terminology of this problem. Now, I need to know that nitrate is NO3 minus 1 to make this work, okay? Now, another thing that I have to be conscious of is it's lead 2, cations plus 2. The nitrate ion is only minus 1. So to make the charge balance work, I need 2 nitrates per 1 lead for every formula unit. And then I've got my aqueous lead 2 nitrate. Now I'm going to add that to an aqueous solution of potassium iodide. I was told it was a solution, aqueous solution of the problem. Now potassium iodide. Fortunately, this one's a little bit easier because from the periodic table we can find these elemental ions. Potassium's in group 1, likes to form +1 ions. Iodine is in group the halogens, likes to form -1, +1, -1. And just pair it up 1 and 1. That's my potassium iodide aqueous solution. So these are 2 water-based solutions. If I saw these and if I had beakers of them in my hand, it would look just like I had water in there, basically, because the salt has dissolved up in the water. And the ions have separated from one another and been surrounded by water molecules. So what I'm going to do is just mix these beakers of water together so that all these ions can mix and the potential for chemistry to occur is there. Okay. Now, always write my arrow to denote chemical change. Okay. And in this case, I'm going to form lead 2 iodide. And in the problem, it says that this stuff is a solid. Turns out that one thing that can happen when you mix solutions of ions is the ions can interact with one another. So lead was originally paired up with nitrate and potassium with iodide, but once you mix the ions together and you stir things, because the ions have separated and become hydrated, there's nothing to stop this lead from reacting with the iodide, and likewise the potassium can react with the nitrate. And if you form something that's insoluble, that doesn't dissolve, doesn't hydrate well, then a chemical change has occurred. And that's what's actually going to occur in this case. We're going to make this solid lead iodide. But we need to write a formula for that. Now I know lead is Pb, and I've got lead 2, and I know my I is -1 because as an element, iodine likes to form -1 ions to form iodide, so it can be isoelectronic with the nearest neighboring noble gas. Now we can't change the characteristics of these ions or the charge states of these ions. We have to roll with what we've been given. So the only way to make this work is if I combine these two in a 1:2 ratio, PbI2 solid. That's what I'm going to make. And I'm also going to have potassium nitrate kind of come along for the ride. Potassium is a group 1 element, likes to form +1 cations. Nitrate is one of our polyatomic ions again. It likes to form -1 ion, so +1, -1. You can balance that charge in a 1-to-1 ratio, and this is going to be aqueous because these ions are going to tend to be dissolved in solution, float around the beaker, surrounded by water molecules. Okay, so this is our skeletal reaction then. Lead nitrate, potassium iodide, lead iodide, potassium nitrate. It's a precipitation reaction because the solid is going to form. We also like to call this double displacement reactions because all that's really going on here is that the ions are switching partners, okay? The nitrate was originally with the lead, but now the lead's with the iodide, and likewise the potassium also switched partners. Now it's with the nitrate, so it's a double displacement reaction, okay? That's how we characterize that. So nonetheless, this is what we've got. Now, one thing that I want you to notice when I'm working this problem, notice what I did. I took the names and I wrote the formulas. What was primarily important there, or what was driving my thought process, was that I had to balance the charges and write the correct formulas for my ionic compounds first. Now, this is not balanced yet. This equation is not balanced yet. I had to write the correct formulas first. You have to do that first. You can't decide you're going to make this a 1 or I'm going to make this a 1 to make everything come into balance when you're writing the equation. You can't do that. You have to finish writing the correct equations for the ionic compounds first, then you come back and adjust the numbers out in front, the so-called stoichiometric coefficients, to make it work. Okay, you got to do it that way. You cannot do it any other way. All right, so let's dive in then and take a look. Lots of elements here. Now, how are we going to balance it? What's our strategy going to be? I've been pointing out that it's a double displacement reaction. The ions sort of switch partners. So what's oftentimes convenient for balancing reactions like this is to treat the ions as groups, okay? So one that sort of sticks out to me is this nitrate. The nitrate doesn't really change from the left to the right. Now, some reactions it may change. Maybe it's oxidized or reduced. Something changes with the polyatomic ion. But here it doesn't. So I've got nitrate before, I've got nitrate after. I can almost treat that as a clump of atoms bonded together as a group. And consequently, I see I've got 2 over here and only 1 over there. That's not going to work, is it, right? So what I probably need to do is put a 2 right there. And if I do so, now I've got 2 on the left. I've got 2 nitrates on the right, and 3 that clump. And I brought nitrate into mass balance, okay? So that's a step in the right direction, perhaps, okay? Now, what about other elements? Well, lead, I've got 1 here, got 1 here. That looks pretty good. Okay, good. Now what about other stuff? Well, potassium and iodide. Looks like I've got 1 of each here, and over there I've got 2 potassium, and I've got 2 iodide. So, I guess maybe if I put a 2 here, now I've got 2K here, 2K there. I've got 2 iodide here, 2 iodide here. I've got 1 lead, that's a balance. 2 nitrate, 2 nitrate. Hey, lo and behold, my double displacement reaction now has been brought into balance, into mass balance. I've written the correct formulas. I've brought it into mass balance in a way that this works now, okay? So this is an example for this type of problem Maybe I'll work through one more real fast here. I know the video is kind of getting long because I feel like there's a lot to explain, but I'll let you see one more here from 363. Part B reads liquid disilicon hexachloride. Disilicon hexachloride. Alright, and they said it was a liquid. So notice how fast I can write the equation for disilicon hexachloride. And this one's a little bit easier, I guess, because it's a covalent compound, so you can use the prefixes. But it reacts with water. Okay, so water, H2O, it's a liquid, to form, so chemical change arrow, solid silicon dioxide. Silicon dioxide, solid, SiO2. What else are we going to make? We're going to make some hydrogen chloride gas and hydrogen gas. Okay. Notice when I added in these, the hydrogen chloride gas and the hydrogen gas, I use G to denote the state. Another thing that I did here almost automatically, notice I wrote H2 gas here. Hydrogen is one of our diatomic gases when it forms typically in nature. So I can't write just H by itself, I have to make it H2 because when we make it, that's just how it's done in nature, okay? It comes off as H2. So I have to honor that, okay? I can still adjust the number out in front, I'm probably going to have to do that, but got to make hydrogen gas. This is how hydrogen gas is packaged. Chlorine's like that, fluorine's like that, oxygen, nitrogen, so on and so forth, okay? I've also got my HCl gas. This is hydrogen chloride gas, okay? You may recognize HCl and say, oh, isn't HCl hydrochloric acid? Only when it exists in aqueous solutions. So to make hydrochloric acid, I have to take this gas and bubble it through water. If I did that, I would make hydrochloric acid. But HCl can also exist as a gas. In such a case, it's called hydrogen chloride gas. It's not quite the same, okay, in terms of its chemical properties. Alright, so with that said, just a little bit of background knowledge for you. I've written out the equation. We now need to balance this. What jumps out at you right away? Well, what silicon does for me. I've got one source of silicon, one place to put it on the right. So I'm thinking, well, maybe I need to put a 2 right here to bring the silicon into balance. The next thing that kind of jumps out at me is the chlorine to a certain extent, I guess, in that I've got one source, one sink. So it seems like it'd be pretty convenient to put a 6 right there and bring my chlorine into balance. So now I brought 2 of these unusual elements into balance, and I can concentrate more on the oxygen and hydrogen. At this point, what just popped in my head is, oh, I am lucky because I've got this hydrogen sitting by itself. I can put whatever number there I want to bring this into balance. So I could probably look at doing oxygen first and then coming back and doing hydrogen last. Okay, so where am I at on oxygen? Right now I've only got 1 on the left-hand side. I may need to change that because it seems like I've got more than that on the right. No oxygen here. In fact, the only place oxygen's at is here. I've got 2 copies of this, which means I've got 4 oxygen atoms, 2 times 2, because every copy has 2, and I've got 2 copies, so 4 there. To bring oxygen into balance, I need a 4 right there. But if I do that, I am in business, and now the only element I've got left is the hydrogen. On the left, it looks like right now I've got 8 H's. What about over here on the right? There's none there. It looks like there's 6 atoms here, and there's 2 more here, which makes 8. So in fact, if I just leave that a 1, I'm in business, and I'm done.